Hello there and welcome back. In this video we're going to continue our discussion of probability mass functions, PMFs for short, for discrete random variables. So recall a probability mass function, Px of x, so capital X is the random variable and little x is the value that capital X can take, has a few properties associated to it. The sum across all of those probability values must come out to 1. It's pretty much like the sum of all of the partition events in a sample space must be 1. The expected value of that random variable x can be found by the sum across all products x times the probability values. Keep in mind sometimes we use mu x to abbreviate this. The variance can be found by doing the second moment minus the mean squared. And keep in mind if you don't know how to find the second moment, or technically even the nth moment, it's going to be found by summing across all powers x to the n. So take all of the x values, exponentiate them by n, and then multiply that by your probability values and sum up all of those products, and that gives you what we call the nth moment. But for variance we only need the second moment, and again sometimes we abbreviate that by sigma x squared, and then you can find the standard deviation by taking the square root of that. So those are just some of the basics for PMFs that you definitely should know. But in this video we're going to go into some particular probability mass functions, and usually we just refer to these as special probability mass functions because they just come up in a lot of applications, so it's usually beneficial to study them in isolation versus the more general PMF properties. So the first concept that we need to understand is, what is a Bernoulli trial? Some people say Bernoulli or Bernoulli, depends on your language interpretation of the word, or the name rather. So a Bernoulli trial is one that can either be represented as success or a failure. There are several parallels to this. For example, either 1 or 0, either true or false. And that of course motivates the reason why we consider flipping coins. For example, we only have two outcomes, either tails or heads. So any type of outcome or trial that has only two outcomes, that is usually what we refer to as a Bernoulli trial. So the very first special probability mass function we're going to be discussing is going to be called the Bernoulli distribution. Bernoulli probability mass function. So suppose the probability, of event, let's call the event E, is equal to, let's call it just lowercase p. Then we can say that the probability of event E is going to be equal to p, and the probability of E not happening, or the E complement, is just going to be 1 minus p, right? So either E happens or E doesn't happen. So if we just focus on this particular event E, then that is in itself a Bernoulli trial, if we just focus on its occurrence. So how do we define a Bernoulli probability mass function, or a Bernoulli random variable? So we go about it this way. So we're going to define x to be equal to 1 if the event occurs, and we're going to define x to be equal to 0 if E complement occurs. All right? So in terms of graphs, what does this look like? So if the probability of success is higher than the probability of failure, so if this is 0 and this is 1, technically that should be reversed, right? So the probability 0 would be 1 minus p and then p. But technically it could be reversed. It need not be in that order. For example, we could have 0 and 1 here. Let's do, I don't know, so 0 could be up here. 1 minus p could be there and p could be here. There's no reason why that cannot be the case. Because sometimes the probability of something not happening is more likely than it happening, and vice versa, of course, right? So the Bernoulli trial could be either this or that, or technically if you consider the heads or tails example, for example, the probability of P or an event happening and not happening are actually both equal to 50%. In that case, you have a distribution such as that, right? And which looks like a sort of a flat or rectangular or uniform distribution. But generally, the Bernoulli probability mass function takes these three possible shapes, right? And generally speaking, we usually don't work with the probability mass function on its own, right? But this is in fact what it is. So we usually write this graph, P capital X of X, is going to be equal to 0 if E complement occurs, or 1 if E occurs, right? So capital X will be referred to as a Bernoulli random variable. It either happens or it does not. But usually we just keep it there. There are some theoretical things you can do with this, but we're just going to be focusing on the practicality of these things now. And let's just move on to the second distribution, which actually has a couple applications that you could associate to it. And also we've looked at a couple applications already that use this distribution. So this is going to be called the uniform probability mass function. So let's assume that S can take one of the following values. So 1, 2, 3, 4, all the way out to some number n, where n is going to be some natural number. So if you consider rolling a six-sided dice, for example, then we might be able to use a uniform probability mass function for that. So the Uniform Pmf has a finite support, so only a finite countable number of things, for which the values are equally spaced, so 1 to 2, 2 to 3, 3 to 4, n minus 1 to n, and so on. So the Uniform Pmf has to have this type of structure in terms of its domain, and the probability that x is equal to 1, the probability that x is equal to 2, all the way out to the probability that x is equal to n must all be equal. So if the probabilities are all equal and the domain values are equally spaced, then we call capital X a uniform random variable. So if all of these things are equal, well, what exactly are those probabilities going to be, right? So remember, if little letter p is indeed a probability mass function, then the sum of all those probability values must be equal to 1. So that means we have probability of x1 plus probability of x2 all the way out to the probability of xn must be equal to 1. They're all equal, so let's just call that value p. So I have p plus all the way out to p is equal to 1. So how many p's do I have? Well, I have n of them, and that means that p must be equal to 1 over n, right? Which is sort of, not exactly, the length of this interval, right? So therefore, if that is the case, we can write our probability mass function. So the probability that capital X is equal to x is going to be equal to 1 over n if x is equal to 1, 2, 3 down to n, or 0 if x does not equal to 1, 2, 3 down to n. Technically, you can write that as either x is an element of S or x is not an element of S, right? So that is the uniform distribution. And it, of course, has a graph, right? So 1, 2, 3 down to n, 1, 2, 3, 4 down to n, and all of them have the same exact probability, call it 1 over m, right? So those are our probability values. Notice that the shape represents a rectangular distribution or a square distribution depending on the shape, and that is pretty much it. So just a couple properties that one should know. Since x is a random variable, it does have an expected value, a second moment, and a variance. So one can show that the expected value for this is going to be equal to m plus 1 divided by 2, and the variance is going to be equal to n squared minus 1 divided by 12, right? So for at least this type of uniform random variable, you have these two special formulas that always work. Now, some people will define the uniform random variable in a different way. For example, you can define x on the interval a plus 1, a plus 2, all the way down to, say, b minus 2, b minus 1, down to b, right? So instead of taking 1 to n, now we're going to be looking at a to b, so it's just going to be a generic interval. For example, you can roll a six-sided die, but instead of being labeled 1 through 6, you can be labeled like 3 through 8 or something like that, right? So it definitely can be a little bit different. but do keep in mind that these intervals still are equally spaced with spacings of 1. You can change the spacing length, of course, and your formulas will change just a tad bit, but this is at least just a starting point that you can sort of work with. So if you define the uniform random variable on this, then one can show that the expected value of that uniform random variable is just going to be equal to a plus b divided by 2. And the variance of this is still going to be n squared minus 1 all over 12, where n is going to be equal to b minus a plus 1. That's pretty much how many points are in that interval if you were to equally space them by 1. Now, how do you interpret this expected value formula? So remember, expected value is practically synonymous to the mean of a data set. So if we were to look at our distribution as a rectangle, then the mean of that, or the expected value, so let's assume that this is our continuous perspective, then the mean should be directly in between, right? Because if that's a and that's b, then the median or the mean should be a plus b over 2. Again, that's not necessarily an element of your distribution. For example, if I have 1 and 2, then that's going to average to 1.5, but it does definitely have some geometric representation. So here's a question for you. Where does these formulas come from? And can I prove these definitions via, for example, the expected value is equal to the sum of x times px, and for example, the variance is equal to the second moment minus the mean squared? Is it possible that I could find these formulas if I didn't know them by hand? And the answer is yes. So what I'm going to do, in case you're interested, is just go through it without speaking, and also put it in a different color background just in case you're not interested in knowing how to prove it. But in case you do want to go through the processes and the algebra associated to it, I will include it here. Enjoy. So now that we have a bit of background on a couple distributions that could be defined as discrete probability mass functions, in particular the Bernoulli and Uniform, one may guess that, these distributions aren't exactly that interesting, or there isn't, realistic examples that would be applied to it. Yes, there are a couple rolling dice problems and equally likely outcomes, and things either happen or they don't, but it's not, not fun word problems, right? So the next distribution will be the first of several distributions that can actually be solved for a lot of different types of distributions and sets the stage for more complex ones. So let's consider a sequence of independent Bernoulli trials. So keep in mind Bernoulli trials, either it happens or it doesn't. And independent means that one trial and its outcome does not affect the outcome of another trial. And let's assume that the probability of success for this particular event is lowercase letter p. And we're going to be defining x to be the number of trials until the first success occurs, right? So what type of sequence are we looking at here? So for example, if I have the sequence failure, 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 success, this is a sequence, let's assume, of independent Bernoulli trials, right? So what would its probability be? So the probability of this particular sequence of events is going to be equal to the probability of failure and failure and failure and failure and failure. 1, 2, 3, 4, 5, 6 failures and success, right? So it's a lot of failures. So a geometric distribution and a geometric random variable are going to be applied to scenarios that can be sort of viewed from the perspective of, if at first you don't succeed, try again until you succeed and then you stop your sequence, okay? So what would this probability be? So since each of these events are independent of each other, I can use just the independent product rule and just write this as the probability of f times the probability of failure times the probability of failure, 6 times, right? So the probability of failure, and then our lonely little success at the end, right? So notice that we are forcing a particular order. It is not one success out of many, it is one success at the very end, right? So this is not a combination problem, this is a particular sequence that we're interested in. So as you already see, this is going to be equal to the probability of failure to the power of 6 times the probability of success to the power of 1, and that is the probability that we get an x value of 7, right? Where x represents the number of trials until we get our first success. So if we're interested in the probability that x is equal to 10, that means we're going to have 9 failures followed by a particular success at the very end, right? So using this type of idea, then we can say that the PMF for a geometric random variable is going to be equal to Pxx is going to be equal to, so what's the probability of failure? So that's going to be 1 minus p, and if x is the corresponding number associated to the success trial, that means there's going to be x minus 1 failures with 1 success hanging out at the end, right? So this is the probability mass function for a geometric random variable. And of course it has an expected value formula, so one can show that the expected value is going to be equal to 1 over p, and the variance of that particular random variable is going to be equal to 1 minus p over p squared. And I'll get into the proof of them in an example just a little bit later. But actually, let's do a real-life example problem for this, and also let's look at the graph of this. So keep in mind, p is a number between 0 and 1. That means the probability of failure also is going to be a number between 0 and 1. So if this number is in between 0 and 1, and we know that this is an exponential function, then this is an example of exponential decay. So if we look at the graph of this particular probability mass function, so 1, 2, 3, 4, 5, and so on, remember, we need at least one trial for a success to occur, so the domain of a geometric PMF is 1 to infinity, but only the integers. So we're going to have the highest value, and then it's going to slowly decay to 0, but never reaching it, just decaying to 0. All right? So that's the graph of a geometric random variable probability mass function. So let's look at a real life example of where you might be able to use this. So let's just pause the video and then we'll get into the problem. All right, so suppose that on average, 27% of people pass a driving test with a particular instructor. Some instructors are really mean, they have bad days, they have bad attitudes, they just don't like people, right? So let's just assume that this is one of those types of instructors. Let's assume that each test attempt is independent from the other. Usually for tests, usually if you fail a test, usually you have some insight that will increase the likelihood of passing on the second. But let's just assume that it has no relationship to your background and experience. It just has everything to do with the particular instructor's mood. So if each test is independent from the other, what is the probability that it will take you 5 attempts until you pass? Assuming no other things like this instructor has a grudge against you or something like that. So this is a particular scenario where we can use the geometric distribution to solve our problem. So we want to only take 5 attempts until you pass, right? So that fifth attempt is going to be our success. So we're going to be interested in the event fail once, fail twice, fail 3 times, fail 4 times, and then finally pass. So this is a happy day. We're assuming that each test is independent from each other, so that means this event is going to be equal to the probability of failure to the power of 4 times the probability of success. So on average, 27% of people pass the driving test. So that is going to be our probability of success. So that means our probability of failure is going to be 1 minus 0.27 to the power of 4 times 0.27. And then once you work this out, what is that going to be? That's going to be 0.73 to the power of 4 times 0.27. You should realize that that's going to be approximately equal to 0.0767, right? So about a 8% chance of passing by the fifth attempt, on exactly the fifth attempt in particular. So keep in mind, since the distribution is increasing, well, what does it exactly mean? Because you would think by the 50th attempt you would have passed, right? So why is the probability so low? Keep in mind is the probability that you pass on that particular one. So since the probability of you not passing until the 50th attempt is extremely unlikely, that's why usually somewhere in here, when the probabilities are like bigger than 10% or something like that, is usually where the highest likelihood or the value for which you expect occurs in terms of your first success. The expected values for random variables can usually help us answer that question. So if you were to, take this driving test, on average, how many attempts would you expect to go with this instructor until you actually pass, right? So what is the expected number of attempts, let's say, for example. So, for example, the expected value for a geometric random variable, remember, is just going to be equal to 1 over the probability of success. So if that's the case, then the probability of success for this problem is 0.27, and you can find that this is going to be approximately equal to 3.7. So on average, you're going to be doing about 4 trials with this particular instructor until you would expect your first success to be. Of course, if you get it on your first try, you're lucky as far as this probability problem is concerned. And if it takes you 50 million tries to get your first success, then you're extremely unlucky based on this first attempt, right? Because keep in mind, since this is an always increasing distribution, this is definitely a skewed right distribution, so the mean definitely should be over here somewhere and not in the middle of infinity divided by 2, whatever that number is, right? So this was where your expected value is, somewhere around here, and this is one application of how you can use that expected value to solve your problems. So again, for a geometric random variable, we have that the expected value is going to be equal to 1 over p, and the variance, and we're going to get into applications of variances of random variables later, is going to be equal to 1 over p squared. So again, one could ask the question, where do these formulas come from? Can you prove these things from the definition? And the answer is yes. So I'm going to close this video with a just algebraic demonstration of how to prove at least the expected value, the starting point for the second moment, and then how you combine those values for the variance, and then we'll do some bonus end of video exercises as usual, just to test your knowledge. Anyway, I hope you enjoy, and I hope you have a wonderful day. Take care.